The condition of identifiability, the very concept of identifiability is nothing very special to linear models. It is true for any statistical models, but in this special case of linear model, it turns out to be the following linear algebraic condition: C prime beta, this linear parametric function of beta, is identifiable if and only if that C belongs to the row space of X. So that is the condition of identifiability. If C does not belong to the row space of X, it is just a meaningless problem to try to estimate it. Howsoever technique you try to use, it's just a meaningless problem, something like estimating beta 1 when beta 1 is always present as beta 1 plus beta 2. On the other hand, we also saw that if C belongs to the row space of X, then you can get some way of estimating it just by taking appropriate linear combinations of those rows of X using which you can express C. So we immediately get another consequence that we have already discussed. It says that if that is the case, in that case there exists some linear combination of the data whose expectation will be that C prime beta. We have already seen that, but just let us remind ourselves how we got that. We did it in this way. Suppose I take this simple case, y1 is beta 1 plus epsilon 1 and y2 is beta 1 plus beta 2 epsilon 2. And my job is, say, to estimate beta 2, which means I am working with C prime beta, which is beta 2, that is C is here 0, 1. Now how do you go about doing that? You can immediately see that I can take the second equation, from it I will subtract the first equation, beta 1 will get cancelled, so I will get y2 minus y1, and that will be an unbiased estimator of beta 2, because epsilon 2 minus epsilon 1 will have mean 0. Both the epsilons have got mean 0. Linear algebraically, what I may say is this thing. So this thing is that 0, 1, that is my C here when I am trying to estimate beta 2, and this is my design matrix 0, 1, 1, 1. So I expressed this as a linear combination of the rows, namely this I multiplied with 1 and this I multiplied with minus 1, I added, subtracted the first row from the second row. I play the same trick on y. Take y2, from it subtract y1, and that will give you an unbiased estimator of beta 2. That is precisely what I am saying. You can find a v. In my case, the v will be plus 1 here and minus 1 here, 1 minus 1, such that take the linear combination of y with those coefficients, expectation of that will be C prime beta. So that's a very good news. Whenever you have something which is identifiable, linear parametric function which is identifiable, you know it is a meaningful thing to try to estimate this, but immediately you also get at least one way by which you can actually estimate it using a linear function of the data, and that estimator will also be unbiased. Not necessarily the best or anything, but at least you have one way of doing it. So we call such a thing linearly unbiasedly estimable. So identifiable turns out to be synonymous with linearly unbiasedly estimable for linear models. I said synonymous, so though I have put this one implication, it is rather trivial to check that the reverse implication also holds. So if it is identifiable, then immediately you have a way of estimating it linearly and unbiasedly. Now this linearly unbiasedly estimable concept occurs so very frequently in the world of linear models that we tend to drop these two adjectives, linearly and unbiasedly. These are not really adjectives, these are adverbs. So we just drop them, we just call them estimable. So whenever you hear the term estimable in a linear model context, you understand we are talking about linearly unbiasedly estimable, and that is equivalent to this being identifiable. So if it is meaningful to estimate it, you can estimate it linearly and unbiasedly.